So the intermediate value theorem starts out as that, and now I can start to draw the picture so we can make sense of what's left here. I have a value A, I have a value B. And the function is continuous. This would be f of A, and this would be f of B. It says that there's a number between f of A and f of B. So I need a volunteer. Somebody, going once, twice. Duets, thank you. So Duets, you tell me. You tell me when I get to a spot that you want between f of A and f of B. You just tell me when to stop. Okay. So he's choosing that n is right there. Okay. Let n be a number between f of A and f of B. What the intermediate value theorem says is this. If the function is continuous, then there must be a corresponding value c between A and B such that when you plug c into the function, you get n. Real life application. I want to drive from Albert Lea to Duluth. No traffic, 4 hours. Somebody's got a lead foot. Okay, so name a city I gotta drive through. Now I can get there without driving through Minneapolis, right? I guess you could try to drive around it, but the idea is that in terms of longitude and latitude, you're gonna have to cross over Minneapolis, right? Yeah, at some point you'll be south of Minneapolis, and at some point you'll be north of Minneapolis, so at some point you're gonna have to cross over that Minneapolis area. Everybody agreed? Okay, so this is the idea. Let's look at it in terms of a function. You don't have to write this down, but if I have this A and this B, okay, we got f of B, which is up here, so some point up here, and I've got f of A, which is right here, and I got some value n, okay? What I would like to do is I would like to get from this point to this point, but not cross that line. How's that? Why does that not work? The definition says it has to be continuous. That was not continuous. Bad, Mr. Gens. Okay. All right, I'll try again. Now I'm going to draw a continuous one that makes it. Do you see how? Oh, that would be cheating, you guys. You get close, then you back away. You get close, and you back away. You go around the side, and there you got it, okay? That's not even function anymore, is it? I mean, it doesn't even pass the vertical line test. Forget it. You can't do it, can you? If you want to get from here to here, you got to cross over n. That's all there is to it. And then there will be a value c within that interval that satisfies that. Let's try an example, okay? So it says, explain why the function has a 0 on the given interval. What does it mean to have a 0? What does it mean to have a 0? So when you plug something in for x, you get an output of 0. So I'm going to show that as a 0 on that point. First of all, it's a polynomial, so it's continuous. F of negative 2 is, what do you get when you plug in negative 2? Negative 2 to the third is negative 8 minus 2. You get negative 8. What is f of 1? 4. Somebody tell me why that tells me I have to have a 0. Yeah, you go from negative to positive. If you're going from negative to positive, you must cross over 0, right? So this is what you have to write. The IVT, intermediate value theorem, IVT, guarantees a value C in what interval? What's the interval? -2, 1, such that f of c would be equal to 0. You try the same thing for b. Go, make sure your calculator is in radians. What was f of 5 pi over 4? Maybe 0.3? Okay, so you'd say the IVT guarantees a value c in 0 to 5 pi over 4 such that f of c is 0. Got it? Okay, let's try another one. We'll look at that in a second here. Okay, it says verify the IVT guarantees a value or a 0 in the interval -1, 2. Find the 0 by using a graphing calculator. So we start by f of -1. Plug in -1, what do you get? 1, very good. F of 2 is 16 minus 4, 13. Does it cross over 0? No, so the IVT does not apply. We don't guarantee a 0. There might be one, but you can't guarantee one. It's as simple as that. So then we move on. F of -1. -4 divided by a -1, or positive 1 is -4 plus 1. Yep, -1, very good. F of 2 is 2. Does that guarantee a 0? Yeah, it sure does. Let's find that 0 using our graphing calculator. Let's plug in our calculator. -4 divided by the quantity x plus 2. Okay, and I'm going to go second calculate, and what do I want to calculate? Number 2. So it's going to graph it, and does it look like the function crosses 0 between -1 and 2? Yeah, it does. So I go to the left. It's the asymptote. It's not actually part of the graph. Your calculator is an 84. It's smarter. Mine's dumber. It's an 83. So mine includes it. All right, folks. Go get some brain food. Come on back. No. Okay. Verify the IVT applies. The intermediate value theorem applies to the indicated value C. And then find C guaranteed by the theorem. What are you talking about? We found C. C is equal to -2/3. Yeah, we plugged in our calculator. Yeah, here, I'll do it right now. Look, y equals that, and then I go second calculate, and I press 0, and I go to the left, and I go to the right, and I find my 0. And does the 0 exist between -1 and 2? Yes, -2/3. A plus. Awesome sauce. Now, where is this function undefined? Where is it discontinuous? At -2, right? Hey, does -2 fall in the interval? No, if it did, then it would be discontinuous over the interval, and the IVT would not apply. So we want to make sure it's continuous over the interval. Look at the next one. Okay, this is a polynomial. Polynomial is defined for all real numbers. Okay, it doesn't have any discontinuity to it. It says f of x equals x squared plus 4x plus 1. We want to know, is there a spot where f of c is equal to 6, where it has an output of 6? Well, let's check. Let's try f of -1. If we plug in -1, we get -1 squared is 1, minus 4 is -3, plus 1 is -2. If you try f of 3, we get 9 plus 12 is 21, plus 1 is 22. So is there a spot at which the output is equal to 6? Why? Because it's below 6 and above 6. If this was, instead of a negative 2, if it was a positive 2, would it still be true? Yeah, it doesn't matter that it crosses over from negative to positive so much as it crosses over 6. So let's find it. We'll take x squared plus 4x plus 1, and we'll set it equal to 6. We want to find where it's equal to 6. Subtract the 6, you get x squared plus 4x minus 5 equals 0. Does that factor? You got negative 5 and positive 1. Did they both satisfy it? Does just one? Did neither one? You tell me. Why just one? Because negative 5 is not in the given interval. So our C value is equal to 1. So there's twice where that function has an output of 6, but only once over the interval of negative 1 to 3. And that's at a value of 1. Got it? Look at the next one. Output of 1. F of 0. Plug in 0. 0 minus 3 is negative 3 squared is 9. So you have 2 over 9 plus 1 is 11 over 9. F of 4. 4 minus 3 is 1. Squared is 1. 2 over 2 is 1. Plus 1 is 2. Is it guaranteed to have an output of 1? Why? They're both bigger than 1, so IVT does not apply. Oh, sorry. Yeah, so 4 minus 3 is 1. Squared is 1. 2 divided by 1 is 2. Plus 1 is 3. Thank you. Yep. Because both of these are bigger than 1. You would need 1 to be less than 1 and 1 to be greater than 1. Look at this here. Negative 2 is less than 6. 22 is greater than 6. That's why there has to be a C value that satisfies the output of 6. Yep. All right. Let's do number 5, then we'll go back to number 4. It says, now we're going to do a proof. I know you love proofs. Catherine has a big smile right now. It's just, she saw a proof and she's like, joy. My day is fulfilled. And I'm happy for that. There's a number that is exactly 1 more than its cube. So give me a number. 1. Is 1 equal to 1 more than the cube of 1? No. So 1 is not true. Try another guess. 2. 2 equal to 1 more than its cube? No. That didn't work. Do you think there's a number that actually exists? I think that there is, and we'll prove that there is. We want to find a number that is 1 more than its cube. Everybody agree that that's an expression that relates that sentence? So I'll subtract the x over, and I'll get 0 is equal to x cubed minus x plus 1. So in other words, I can guarantee that there's a number that satisfies that equation if I can find an output less than 0, and if I can find an output greater than 0. So I'm just going to try a value. I'm going to try f of, let's try negative 3. What's negative 3 cubed? Negative 27 minus negative 3. Negative 24 plus 1. Negative 25. Now I'm going to try to get a value. Oh yeah, negative 23. Okay. So, and then I'm going to try f of, we'll try 1. 1 to the third. 1 minus 1 plus 1. 1. Okay. Well, I have an output less than 0. I have an output greater than 0. So does there have to be a number between negative 3 and 1 that would give me exactly 0? Yeah. So The IVT guarantees C in the interval. What's my interval? -3 to 1. I just chose -3 and 1. If you chose -3 and 2, it would still work, or -2 and 5. Chose C in -3, 1, such that f of C is equal to 0. Now, you still might be kind of wondering what that number is. It doesn't say to find the number. Our proof is done. We've proved it. There has to be a number. And to show you that the number exists, I'll quick find it for you. X to the third minus x plus 1. I'm going to graph. I'm going to find where it crosses that 0 spot. That's the number. So like, does that really work? Well, that number is supposed to be one more than its cube. So I'll take negative 1.3247 and I will cube it. And then I will add 1. Did I get my original number? Yeah. So that's the number that's exactly one more than its cube. Proved it. Last example. Excellent. Keep trying. All right. Show that the following function is continuous for x equals 1. This is what we did yesterday. Continuous, continuous, continuous. What is the first thing that we must be able to figure out to satisfy continuity? F of A exists. So it says show that's continuous for x equal to 1. So f of A must exist. What's the second condition we must satisfy? The limit as x goes to a of the function exists. And then the third is that the limit must equal the actual output. And if that's true, then the function is continuous at that given spot. Which is beautiful because now we'll be able to prove continuity of graphs, for all real numbers. You could literally pick any number and show that continuity is there, and it has what we call nice behavior. So let's look at these examples. And here we have a piecewise function. We want to prove continuity for x equals 1. Let's see if we can check off the first box. Does f of 1 exist? If you plug in 1, what do you get? Yeah, this tells me I get 3. So now what we want to do is we want to check to see if the limit exists. Well, in order for the limit to exist, I must check the limit from the left, and I must check the limit from the right. So if you look here, this is a piecewise function. It's equal to negative x squared plus 4 from the left. It's equal to 1/2 x plus 5/2 from the right. So if you were to come up with an endpoint here, you would plug in 1, and what would your output be if you plugged in 1? 3. So if we were to make a graph, which I won't do for the entire piece, but negative x squared plus 4, you would have an open circle at 1, 3, and that would be that part of the graph, right? So you can see that the limit is 3 from the left. Well, let's check the limit from the right. If you were to plug in 1 here, what would you get? You get 1/2 plus 5/2 is 6/2, which is 3. So you would get a graph like that. So that limit is 3. And also notice that when you plugged in 1, you got 3. So is this function continuous? Yes. The output exists, the limit exists, and the limit is the same as the output. So therefore, this function is continuous. It's not necessarily the prettiest looking function, but it is continuous. Okay. All right, that's it. We show this continuous just by doing these three pieces. So we stated these three, and we now satisfy them right here. So we're good. All right, I got a worksheet for you.